So in this video, we're going to find the area bounded by the graphs of the cosine and sine functions. And the idea is the graphs of the cosine and sine functions intersect each other infinitely many times, and we get regions that look like this or are a reflection of this region, and these bounded regions have the same area. So we have infinitely many areas that are exactly the same. What we want to do for this example is just find the area of one of the bounded regions. So we're going to find the area of this bounded region right here. So what we want to do is recognize that we're going to need to find the two intersections. That's one thing that we're going to need to do. We want to recognize that the function that's bounding from above is actually the sine function. So this is the sine of x. And the function that's bounding from below between this intersection and this intersection is the cosine of x. So we want to recognize the bounding above function and the bounding below function. And then we want to recognize that if we do a representative rectangle, it's going to be oriented vertically between the two bounding functions. So we're going to have dx's will be integrating with respect to the x-axis, and our heights are going to be a delta y. So the distance between the two functions will be a delta y, or a y2 minus y1 kind of thing. So the first thing we want to do is go hunting for these first two intersections. And what we want to recognize is that those intersections are going to occur when the two graphs are equal to each other. So if we set the sine equal to the cosine, we set the two functions equal to each other, and then we try to solve for the intersection points. So the next step here would be to divide both sides by the cosine function, and if you divide by cosine on this side, you get 1, and sine divided by cosine on this side is just going to be the tangent function. So we get tangent of x is equal to 1. So x is really going to equal, there would be infinitely many intersections. So x is really going to equal the arc tangent of x. We take the inverse tangent of each side, and those solutions are going to repeat themselves every pi times k, where k is an integer. We want to recognize that the inverse tangent function will have solutions that are pi radians apart from each other on the input axis. We really only need to find the solutions on the interval from 0 to 2 pi though. So here's 2 pi sitting right here, here's 0. We really only need the intersections on the interval from 0 to 2 pi. So I'm not going to worry about the fact that there's infinitely many intersections. We just need to think through what's going on. So if we look at the unit circle and think about it for a minute, we know that at pi over 4 radians, we have the ordered pair on the unit circle, square root of 2 over 2, comma, square root of 2 over 2. And on the unit circle, this is the cosine, and this is the sine. So sine over cosine, or tangent, is going to equal 1 at pi over 4 radians, because the x and the y coordinates are the same. When we take the ratio, we get 1. So we're going to get pi over 4. That's the first x location of this intersection. This is going to happen here at pi over 4 radians. And then we're going to get a 1 again over here in quadrant 3, because if we reflect through to the angle 5 pi over 4 radians, we get negative root 2 over 2. The x and the y coordinates are both negative in quadrant 3, so the ratio is going to be a positive 1, because we'll get a negative divided by negative is a positive 1. So the second place where we're going to get the intersection on the interval from 0 to 2 pi is going to be at 5 pi over 4 radians. So right here, this is going to be 5 pi over 4 radians. So now it's just a matter of setting up the integral. So it's going to be the integral from pi over 4 to 5 pi over 4. And then the bounding above function is the sine function, so it's going to be sine of x, minus the bounding below function, which is the cosine of x. And this is going to be dx, so we go ahead and integrate. So if we integrate sine, we get minus the cosine, minus the antiderivative of cosine is sine. And we're going to evaluate these over the interval from pi over 4 to 5 pi over 4. So we're going to get minus the cosine of 5 pi over 4 minus the sine of 5 pi over 4 minus, parentheses, the opposite of the cosine of pi over 4 minus the sine of pi over 4, running out of room there. And the cosine of 5 pi over 4 is just the x-coordinate here. So you can see the sine and cosine of 5 pi over 4 are both going to give us negative square root of 2 over 2. So we get the opposite of negative root 2 over 2 minus the opposite of the square root of 2 over 2 for sine of 5 pi over 4. Minus minus, a double negation gives us plus, and the cosine of pi over 4 is just the square root of 2 over 2. Minus minus double negation gives plus, and the sine of pi over 4 is also the square root of 2 over 2. So we get some double negations going on here. That's going to give us a plusy, and this double negation right here will give us a plusy. So we see we get the square root of 2 over 2 4 times, so 4 roots of 2 over 2, which is just 2 times the square root of 2.